Before we start to discuss spectroscopy, I wanted to make sure that we fully understand why we use instruments and machines to excite electrons in order to observe things about atomic structure. So I'm going to take you to this website. It's posted as a resource. So you can actually explore it yourself. But I like this simulation because it forces us to go back and review the basics as to what happens to electrons when we excite them. So most instruments and most things that measure atomic structure involve sending some kind of light to an atom, causing electrons to get excited in some way. The electrons that are excited then can relax back down to an energy level that's lower, and they release lights in the process. So you can see in this process, I'm exciting an electron up to the second energy level. It's actually getting excited into a dumbbell-shaped orbital. It's unstable there, and then it releases another type of light, which is then caught by a detector. That's the basic theory behind how spectroscopy works. So we did an experiment in sophomore chemistry where we actually excited the electrons of different atoms, and we got different colors that we looked through a spectroscope, and we used a prism to separate all of the colors that are being released by excited electrons, and that's called an atomic emission spectrum. So the one for hydrogen is very simple because there's only one electron that's really getting excited in the different energy levels. Electron gets excited by the electricity being run through it. It moves to a higher energy level. It's unstable in that state, and it drops back down to other energy levels, releasing different colors of light. So hydrogen's is the simplest, and then we get to elements like neon and mercury, and they get more complex because you have more electrons doing this. There's more energy levels involved in that process. Every element has its own unique signature of colors, too. There's certain limitations, though, to atomic emission spectrums, and that's because it only gives us information about the energy levels of the electrons. It doesn't give us information about the specific sublevels that the element's electrons reside within. It just tells us, oh, the electron transition from energy level 3 to 1, and that's it. Photoelectron spectroscopy, however, gives us more detailed information about the sublevel in which the electrons reside. So we're going to focus a little bit more on photoelectron spectroscopy since it's the more likely type of spectroscopy that you're going to see on the AP exam. Don't forget that ionization energy is the energy required to remove an electron from a gaseous atom or ion, basically to take it from the n principal quantum number energy level all the way to infinity, which means it's left the atom completely. It's very unlikely that we can remove more than 5 electrons from a single atom at a time, so we need a better way to examine the electrons that are in these various sub-levels. So that's where PES comes into play here. How does it work? Just like I showed you before, we take high energy light, usually X-rays or sometimes UV light. It shines on the surface of the elements. The atoms release electrons. This is the photoelectric effect, right? It ejects electrons depending on the energy of the photon. And it's a quantum event, which means it's based on probability. We're actually going to go through in class a simulation which shows you how this works in motion. But we measure the kinetic energy of the ejected electrons, and we can use that kinetic energy to make an estimation as to what the binding energy was, which means the energy that was holding that electron in place. Different subshells of electrons are going to have different attractions to the nucleus depending on the level of shielding, how far they are away from the nucleus, so on and so forth. A basic PES readout has 2 components to it. The bottom axis sometimes is inverted, and it has numerical quantities in megajoules per mole as to how many total megajoules per mole it took to eject that batch of electrons. The y-axis is going to give us a count of the relative number of electrons that were released at that binding energy. What we're going to do is we're going to be able to use these peaks to start to map out sublevels of the elements in question to be able to make a determination as to what it is. Usually this y-axis is labeled, but for this example, we just are saying, okay, well, this peak is half as big as this peak, so we can assume that twice as many electrons were removed here as here. Now, if you look at this axis, this peak has electrons at a higher bonding energy. That tells me one thing, that those electrons are probably closer to the nucleus and they're less shielded because they're being attracted to the nucleus more. And those electrons are actually our 1s electrons. There's two of them. The next peak is probably the next batch of electrons that's a little bit further out, and the next set of sublevels that comes after 1s is 2s. But since the relative intensity was 1, 2s1, piece together this entire picture, and we've got the fact that we're dealing with lithium. You can also count the total number of electrons to help you read these. Okay, here's another PES diagram, starting with the highest binding energy. There's 2 electrons here, so that's probably my 1s peak. Moving over to the next set of peaks. The next highest binding energy is the next one that's closest to the nucleus, so that would be my 2s peak, and there's 2 electrons there. You can see that these peaks are grouped together because they're actually very similarly distanced from the nucleus, but we said that the 2s electrons shield the 2p electrons just a little bit, which causes the 2p electrons to have a slightly lower binding energy and less attraction to the nucleus. So you can see that this element would be boron. This is another readout for sodium, and you can start to see that our peaks begin to split. 1s, 2s. This peak is 3 times as big as this one because there's 2 electrons here. So these are 6 electrons in my 2s, or I'm sorry, my 2p. And then my 3s valence electron is held with the least amount of binding energy because of all the shielding of all these interior core electrons. So we're going to take a second and we're going to practice interpreting these PES diagrams. This is a good multiple choice question taken directly from an AP exam. I would like you to take a moment and see if you can answer this question. This is a very common type of question because you can see that you have multiple choice, but it's really about the justification for the correct answer. And we're focusing on the 1s peak, and it's saying which of the following identifies the 1s peak for fluorine compared to carbon. Well, the key is fluorine and carbon are in the same period together, and fluorine has more effective nuclear charge. So that's kind of what I'm looking for in my answers. Well, it looks like letter B might be the correct answer. And let's double check. Peak X has a much higher binding energy than peak Y. So it would make sense that fluorine's 1s peak would be more tightly bound because of the higher number of protons increasing the effective nuclear charge. So letter B is actually our correct answer with the correct justification. So that's a very common type of multiple choice question you'll see with peaks from a PES diagram. This is a quick review of the different types of spectroscopy. We're actually going to go back and we're going to review a lot of these in greater detail when we get to labs that involve different types of light. The biggest thing to know is that PES uses X-rays, and it's better for identifying sublevels. So it's better for identifying whether the electrons are in 1s, 2s, 2p, and giving that detailed information. UV Vis is used for UV Vis spectroscopy, which we're going to learn about in greater detail. The biggest thing about UV Vis spectroscopy is when we use the types of light in the UV visible range, it excites the valence electrons, but really it just gives information about which energy level the electrons are within. It doesn't give us the detailed information about sublevels. Infrared and microwave radiation are less common, but there are questions that do pop up about just understanding the facts or understanding the purpose of each type of spectroscopy. Infrared radiation is more important in determining vibrations within actual chemical bonds, kind of like little springs. Chemical bonds vibrate when they're exposed to infrared radiation, and infrared spectroscopy is more useful to be able to determine the types of chemical bonds, whether it's a double bond, carbon connected to an oxygen, things of that nature. Microwave spectroscopy is better for determining the locations of hydrogen atoms within a molecule because microwaves rotate atoms, and rotations are more useful for determining the locations of specific hydrogen atoms. UV Vis spectroscopy relies on the fact that I can get electrons excited to higher energy levels and cause them to then drop back down. And then I can read in my spectra which wavelengths are causing these transitions, and I can use this to measure concentration, but that's going to be a topic for a later day. Infrared spectroscopy, IR, is better for determining different types of chemical bonds. Usually the axis will look something like this with the wave number in centimeters inverse versus the percent transmittance. These peaks will be kind of upside down, and they determine different stretching energies for different types of chemical bonds. So for instance, a C connected by a double bond to an oxygen specifically occurs in this wave number range. A C triple bonded to an N or a C triple bonded to a C occurs right here, so on and so forth. So this can give us detailed information about the types of chemical bonds that exist within a sample. Rotational spectroscopy, not as common, but it causes atoms to rotate, and it can give information about the positions of hydrogen atoms that are rotating within molecules in a particular sample. Our final topic is going to be a quick review of periodic properties, but hopefully that was a helpful summary of all the different types of spectroscopy that you need to know.